Okay, so conic sections, which is what this entire chapter about, is what's going to occur when you take a cone, or in the case of a hyperbola, what's called a double napped cone, but we'll talk about that one later, and you slice these cones in different ways. So if you see, I have these shapes up here in my hands. I'm going to put my iPad down and then show you. I have these shapes in my hands. This is a cone. Yes, we agree, it's a cone. If you took a plane and chopped it, or like took a knife and you chopped this cone in a diagonal way, like you just took the top off of it, it would look something like this, right? Where I like took the top off of the cone. If you look at the top that I've created, that has created this oval shape on the cone. This is called an ellipse. So this entire unit is called conic sections because you can take a cone and chop it in different ways to create these different shapes. So if you chop it with a flat line, you would create a circle if you looked down at the top of the cone. Easy, we don't even have a lesson over that one because it's just a specialized ellipse. An ellipse is created, it's like an oval, when you chop the graph or chop the cone in a diagonal pattern. So we have created an oval out of the conic. The next one we're going to learn about is called a hyperbola. This one requires a double napped cone. So you would have a cone on top of another cone and slice it straight down. Do you see how it creates like a U-ish shape one direction and it would create a U-ish shape another direction? That's called a hyperbola. And then last but not least, if you take a diagonal chop that doesn't go all the way through it, just halfway goes through it, it creates a parabola on the cone. Sorry. It creates a parabola on the cone. These are the shapes that we are creating out of these conic sections. What we're going to do in this unit is go piece by piece and talk about the different characteristics, equations, and vocabulary involved in the three different conic sections of ellipse, hyperbola, and parabola. Okay? Today is all about the ellipse. So your first thing right here is the ellipse. We're going to go first through vocabulary and then work on the equations for these ellipses. So an ellipse is a set of all points P in a plane, the sum of whose distances from two fixed points F1 and F2 is constant. So we could create these on a coordinate plane if we took these 2 points right here that are called the foci, which is the plural of the word focus. If there was one of them, we'd call it a focus, but there is 2 of them, so we call them foci. If we look at the distances and sum the set of points equidistant from it, it creates this shape. Or if you think about a conic section and you karate chop it on a diagonal, it creates this oval shape called an ellipse. The midpoint of the segment connecting the foci is called the center of the ellipse. So when we're talking about the center, we're going to be using the color orange. Your center is right here on the ellipse. Yeah, it's all the color coding. The line through the foci that connects the ellipse at 2 points is called the vertices, or singular is a vertex. So if I look at the vertex or vertices of the ellipse, it goes through the center and connects to like the tallest or the widest endpoints of the ellipse. The line segment that joins these vertices is called the major axis. So these points right here, or this line that connects the vertices through the center, is called your major axis. Notice that the midpoint of the major axis is that center of our ellipse. The last vocabulary we have is the line segment whose endpoints are on the ellipse that is perpendicular to the major axis is called the minor axis, and that's just going the other direction across the center. These vertices that connect the minor axis to the ellipse don't technically have a name in our textbook, but I've seen other textbooks call them the minor vertices. So you have your major vertices, or the vertices, which are blue for us, and then your minor axis does touch the ellipse, so you can think of those as minor vertices. But we have all of this vocabulary here for us. We have our vertex, we have our foci, we have our center, major and minor axes, and that's it, and the minor vertices. One of the goals of today is to be able to identify what those pieces are if you can just point at them, right? But once we get all of the vocabulary down, we also want to be able to write equations for these ellipses. So now we're taking that conic section that we karate chopped off of the cone and we're looking at it on a coordinate plane. The standard form of the equation of an ellipse with the center at the origin and major and minor axes of lengths 2a and 2b are as follows. You have two options. We have to keep them separated in our brain. If you have a horizontal major axis, which means that your ellipse is long, then your formula that you're using is x squared over a squared plus y squared over b squared equal to 1. If your ellipse has a vertical major axis, which means it's taller than it is wide, what do you notice about the formula comparing the horizontal versus the vertical? What has changed? The B and the A switch. So what I want you to think about for ellipses is that the A is the major. So if A is major, that means A is always bigger. If the bigger one is underneath the X, that means your X direction sideways is bigger. And if the A is underneath the Y, that means your bigger number is on the height, is on the tallness of it, so it's a vertical major axis. Continuing to label and to color, just kind of giving us some references. The vertices are on, again, that major axis. So we have a major axis here and a major axis here, so that our vertices are A units from the center on both sides of the center, either up and down or side to side, depending on the kind of ellipse you have. The foci are on the major axis, again, that major axis, but this time they are C units away from the center. They're in between the vertices and the center, so they're inside the shape. So we needed to know some sort of relationship between A and B and these foci C so that we can locate the foci, which is one of the big things that we're doing when we get these formulas. It's related to Pythagorean theorem in a sense because it looks very similar, but it is not Pythagorean theorem. Where were we before we went to lunch? Okay, so what we were looking for is some sort of relationship between the values A, B, and C. A and B come from the equation, and C is the location of the foci. So we were looking for a relationship between them. And we can find through some triangle work that b squared is equal to a squared minus c squared, or equivalently, and even more equivalently, this is the one you're going to use, that c can be found by taking the square root of a squared minus b squared. So it's not Pythagorean theorem, although it looks very similar to it. So when I'm going to ask you to find the foci of different ellipses, then you're going to need that formula, a squared minus b squared, take the square root, to find the value C so that we can identify where the foci is. The kinds of questions you're going to be asked is to write equations of these ellipses or use the equations to graph, to plot the different particular points. So if we look on the back, here's what a question might look like. We're going to graph and locate the foci of x squared over 9 plus y squared over 4 equal to 1. Just because I know we're going to need it, I'm going to rewrite that formula down. It's C equal to the square root of a squared minus b squared. That's the formula we're going to be using to find C. So here we go. If we have this formula, x squared over 9 plus y squared over 4 equal to 1, I can rewrite that as x squared over 3 squared plus y squared over 2 squared equal to 1. Which means that since the number underneath x is larger, we know that a is going to be equal to the number 3, and I'm doing that in blue on purpose, which tells, and b is going to be equal to the number 2. And since a is always bigger than b and a is underneath x, that means that we're going to have a horizontal, yes, a horizontal a value of 3 and a vertical b value of 2, which means that our ellipse should be more horizontal than it is vertical. Should be longer on the horizontal than on the vertical. Since we have A and we have B, we can also use those values to find C. Now remember, C is equal to the square root of A squared, which is 9, minus B squared, which is 4. 9 minus 4 is 5. So the C value here is square root of 5. That means for us that the foci can be found at the coordinate point that is to the right and to the left of the center of this along the transverse axis. And since this is a horizontal ellipse, we're going to have the foci be at negative square root of 5, 0, and square root of 5, 0. So what this means, we have a center of our circle at the origin. We haven't started shifting this off the origin yet, so I'm going to put a dot at the origin to represent the center of my ellipse. I'm going to count a horizontal distance of 3 on both sides of that center, and I'm going to put blue dots there. 1, 2, 3, and 1, 2, 3. That is 3 spaces away on my transverse axis, on my major axis, I should say. And then we're going to count 2 spaces above and below that center for the minor vertices. The foci should be inside the ellipse. Which means that these are at approximately, I looked this number up, negative 2.236, and this is approximately positive 2.236, so that we know where we're plotting these points. Since square root of 5, we probably don't know that value. So if I look here, 2.2 something and negative 2.2 something would be here. When we play connect the dots, we are really connecting in a circle the major and the minor vertices, making sure that our foci are in the center and the center is in the center. To re-emphasize some vocabulary for us, we're also going to highlight that major axis. The major axis is the axis that goes across the center on the longest side. So I would highlight green on the horizontal axis to show that this has a longer horizontal length than it does vertical. So some things to remember when it's centered at the origin. The A value is always the bigger number. So if it's underneath X, it's a horizontal. If it's underneath Y, it's a vertical. You find the C value, which helps you determine the foci by doing square root of A squared minus B squared, and then using both the positive and negative version of it for the coordinate points. Feels like we don't understand anything yet. Let's see another example just to see the differences and what a problem could look like for you, and then we can ask some questions on this page. For example 2, again, we're still centered at the origin, but this looks funky. Why does this look funky? Yeah, where are the fractions? How do we do this? Here's something I want you to notice that you may not have noticed before. What is this equation equal to? 1. What is this equation equal to? I need it to be equal to 1. So I need to divide the entire thing by the number 400, so that 400 over 400 becomes 1. Now when I do this, 25 over 400 becomes 16. 16y squared over 400 becomes a denominator of 25. 400 over 400 becomes 1. So again, all I did was actually divide these numbers. 25 over 400 is 1/16, and 16 over 400 is 1/25. Now that it's written like this, where it says equal 1, we can find the A and the B. We rewrite this as x squared over 4 squared plus y squared over 5 squared. And we can answer the questions, what is A, what is B? What is A? A is always larger. So A is 5. But since that 5 was underneath the Y, that means we're going to have a longer vertical side than horizontal side. This is going to be a tall ellipse as opposed to a wide one. What is my B value? 4. That's going to be my horizontal distance from the center. Okay, we still need to find C, A, B, and C. We're going to use that formula from the top of your page where C is going to be equal to the square root of A squared minus B squared. Making sure you actually do A, which is 25, or A squared, and B squared, which is 16. 25 minus 16 is 9, and the square root of 9 is 3. So for this ellipse, our foci are going to be located above and below the center, since we have a vertical major axis. So this time our foci are at 0, negative 3 and at 0, positive 3. When we have the center, both vertices, the major vertices and the minor vertices, and then the foci, we can graph them. This one has a center at the origin, so we go ahead and place our center point at the origin. We are going to count a vertical distance of 5 above. Yes. That is a great question. How do we know it is in the center? 2 ways. The topic is talking about it. Okay, but if we didn't know that, there's no number next to X and Y. And in a second, we're going to start shifting it off of the origin, and you'll see a difference in what the formulas look like. But there will be numbers next to X's and Y's if it's not at the origin. Great question. So we're going to count 5 above this one, above and below for my major vertices, because we have a vertical ellipse. And we're going to count 4 side to side on my minor axis. I'm also going to plot the foci. They should be on that major axis. So in line with the blue dots should also be the pink dots. Your foci should be there in line, blue, pink, and orange all in a line. Once you have all of those things plotted, you can sketch the graph. And I have to do a couple laps to get mine to look circular, or else it looks like a diamond. That's not too bad. And we're going to highlight, just to keep practicing our vocabulary, that major axis is the one that goes vertical this time. It hits at our major vertices. Okay, now that we've seen 2 examples, do you have any questions we want to ask? You're good? Okay. Yes?
How do you know which one is going to be vertical, which is going to be horizontal?
Great question. So the A value in an ellipse is always bigger. In the first example, the bigger number was underneath X. X is a horizontal direction. So since the bigger number was underneath the horizontal direction, it's wider than it is tall. But in example 2, the bigger number was underneath the Y. So it's a vertical major axis as opposed to horizontal. Does that make sense? And those rules are going to change for each conic that we look at. So this is the rules for ellipses. Ellipse. I keep saying ellipses, which is the ... at the end of a sentence. Okay, let's see another example. This time, we're not graphing the function. We're trying to write the standard form of the equation given 2 pieces of information. The information we were given thus far is that the foci occur at -1, 0 and 1, 0, and its vertices, or major vertices, are at -2, 0, 2, 0. That is plenty of information to find the equation. Because to write the equation, all we need to know is the center and A and B. If we think about this, the pink stuff that we've highlighted right here tells us the following information. it tells us that C is equal to 1 because they're both one distance away from the center, and the center would be in between them at 0, 0. That's two things we learned. C is 1, the center is 0, 0. We also learned that this has a horizontal axis, and I know this because the foci have x coordinates. If the foci had numbers on the y, then that would mean it's a vertical ellipse. The blue information having the vertices at -2, 2 tells me that A is equal to a particular number. What number do you think A is going to be equal to? 2. Since the vertices are both 2 distance away from the center, that means my A distance from the center is 2. Now this information is more than enough that I need to solve for B. If you flip back 2 pages, which I won't actually make you do, there's a formula B squared equal to A squared minus C squared on the front page. This is just a solved version of C equal to square root of A squared minus B squared for us to solve. If we plug in what we have, A is 2, C is 1. 2 squared is 4, 1 squared is 1, that's 3. If B squared is equal to 3, then B is equal to square root of 3. It's just a little quick algebra moment. If I have A and I have B, I have enough information to write the equation. The equation should be x squared over some number plus y squared over some number equal to 1. We need to figure out where to put the letters A and B, or the numbers A and B. Since this is a horizontal ellipse, am I going to put the larger number under the x or under the y? The x. So I'm going to put the larger number, which is 2, underneath the x, and I'm going to square it. Then I'm going to put the b value underneath the y, and I'm going to square it. Because it's x squared over a squared plus y squared over b squared. So my formula is x squared over 4 plus y squared over 3 equal to 1. Again, notice that the larger number is underneath x because we know it's a horizontal. Since all of the values of the foci and the vertices have x values and no y values, they're in line horizontally. Now what happens when we start to make this complicated and we don't have it centered at the origin? Now we're going to have additional letters floating around our formulas for us to use. To translate the ellipse, we're going to take the shape that we have and just literally shift it around, moving the center. That is what we're moving. So we have a translated graph that we're going to need. I would highlight this one in yellow, but then on the inside, we're going to highlight the coordinate points that create the center. If you notice, the center of this picture goes from 0, 0 to the coordinate point h, k. Where are they getting the h, k from, you ask? Great question. H is always next to x, k is always next to y, and it creates your coordinate point h, k. So we're going to now have numbers added and subtracted to the x and to the y, similar to when we graphed circles in Unit 2 or 3, whatever chapter that was. And that's going to shift the circle or shift the center of the ellipse around the graph. Now, since we have shifted the center of this graph, it changes where we will find all of our vertices, and most importantly, it will change where we find the foci. Your foci formula is now as follows. You are going to do h, k, but you're going to add and subtract the value c from that k. This is for when you have a vertical ellipse. When you have a horizontal ellipse, just get all the colors out here. Oh, no, that's wrong. This is going to be h plus or minus c, k. So you're now having to add the value we find for the foci, for C, for the foci, to the center instead of just 0, 0. It was very easy when we were centered at the origin because 0 plus C is just C. But now we're adding and subtracting that C value to the center. So let's see how this works. We're going to graph and locate the foci just like we did originally, but this time it's not centered at the origin. It's centered at h comma k. Okay, first things first, let's rewrite this formula so we can see the a and the b. This is x minus 1 squared over 2 squared plus y plus 2 squared over 3 squared equal to 1. Where is the center for this ellipse? It has to do with the numbers in the parentheses next to x and y. Kind of like in point slope form. It's like if you see a negative, it's positive. If you see a positive, it's a negative. This center of this ellipse is at 1 comma negative 2. So the x coordinate is next to the x, and the y coordinate is next to the y. The other things I learned just by looking at the formula is that a is equal to what number? 3. A is always bigger, and since a is 3 and it's underneath the y, that means we're going to have some vertical major axis. It's going to be taller than it is wide. What's the b value? 2. That's my horizontal. But it's smaller, so this is a vertical ellipse. The other thing we did previously was we found C, so we're going to continue to do that. We find C with the same formula, which is going to be a squared minus b squared, which is equal to square root of 5. Now, when I put this together to create the coordinate point for the foci, it's not just that C value like it was before, because we have to change the center that we are adding and subtracting from. We said that this is a vertical ellipse. So we need to add the foci value to the vertical coordinate, meaning we will have foci at 1 comma negative 2 minus square root 5, and at 1 comma negative 2 plus square root 5. Where did all these things come from? Great question. So glad you asked. This is the value of C that I'm adding and subtracting. These are the center points, the center of the ellipse. I chose to add and subtract the C value from the y coordinate because it's a vertical ellipse. For plotting purposes, negative 2 minus square root 5 is approximately negative 4.23. And for plotting purposes, negative 1 plus square root 5 is approximately 0.23. So it's going to give us places to plot these coordinate points. Let's start from the beginning, and let's plot the center first. The center here is at 1 comma negative 2. So now instead of putting it at the center, we're putting it at 1 comma negative 2. The vertical distance, the A value, is 3. So not from the origin, but from the center, I'm going to count up 3. 1, 2, 3. And I'm going to count down 3. 1, 2, 3. We're still just counting up and down, but we're following the center to do this. To make your minor vertices, the B value is 2, so I'm going to count 2 to the left and 2 to the right of my center to plot those points. And last but not least, we have our foci, which is at 1 comma negative 4.2-ish, and at 1 comma 0.23-ish. Again, it should visually be inside the ellipse on the same line as the center and the major vertices. And so we plot these points. That was not great. Let me try again. To double check we put everything where it's supposed to, we look at our major axis and see that all of the points that should line up on the major axis indeed do line up on that major axis. The bottom line with a lot of these questions is if you can find A, B, and C, you can figure out where this graph is supposed to be on a coordinate grid, because if you can control the center of the ellipse and you know A, B, and C, you know everything. That's always our goal. Find the center, find A, B, and C. Are we ready for a challenge? We're doing it anyways. Here we go. I love this kind of question. It sounds scary, but it uses so much fun algebra. So we're going to take this entire equation, we're going to graph it. First of all, does this look right? It does not look like the questions we've been having before, but we can use our skills that we learned in chapter 1 to make this happen. Here's what I want, and I want you to use your small handwriting because it's going to take a bit. We are going to organize all of this mess into the following. We're going to put all of the X's together, and I'm going to put a blank right here. And then I'm going to put all of the Y's together. And then I'm going to put a blank right here. And then I'm going to move anything that does not have an X or a Y to the other side of the equal sign. Since I'm going to add numbers in both that square space and on the circular space, I'm going to leave some space here on this side for those as well. Is this ringing a bell for somebody? Yeah, we did completing the square to right equations of circles way back when. Same vibe, just now these are ellipses and hyperbolas and parabolas. Now, question for you. Did I ever teach you how to complete the square whenever there was a number in front of the x squared? We avoided it because it was hard. Does anyone remember what we did? You can say no. We need to make sure when we're completing the square that a is equal to 1. So what I'm going to do is I'm going to factor out the number 4 from the entire things that have x's. So this becomes x squared and 10x and then my mystery number all in a parentheses. What number would I factor out of the y's? 36, the whole thing. We want the y squared to be by itself. This ends up being y squared minus 8y plus another mystery number, all equal to that negative 532 plus, and this is important, the number you multiplied or you factored out, 4, times the first mystery number, plus the second number you factored out, multiplied by the mystery number. Let's figure out these mystery numbers. When we're completing the square, does anyone remember the cute little pattern that I told you to remember? You can say no, it's been a minute since we did completing the square. It's b divided by 2 squared. So we're going to do 10 divided by 2 and square it. But we're going to show our work on purpose for these problems. My mystery number is 25. I would put a 25 right here. I would zoom over to the other square box on the other side and I'd put a 25. We do the same thing for the y's. This becomes negative 8 divided by 2 squared, which is negative 4 squared, which is 16. So 16 goes in the special box or circle, and a 16 goes in this one. Just as a heads up, what's 4 times 25? 100. And then 36 times 16 is 576. So just so we know what those numbers are for later, I just multiplied them. Okay, let's clean this up. A whole lot is going to happen in one fell swoop. So now that I have this multiplied, those parentheses are going to magically, by completing a square, become x plus 5 squared plus 36 times y minus 4 squared equal to everything on the right side of that equation, which is negative 532 plus 100 plus 576, and if you trust me, that's 144. We are one step away from standard form. We did this a second ago, I think on example 2. What do all equations of ellipses need to be equal to? 1. What is this one equal to? So what should I do with every single piece here? We're going to divide by 144. 4 over 144 is 1/36, so this is x plus 5 squared over 36. 36 over 144 is a fourth, so this becomes y minus 4 squared over 4. And 144 divided by 144 is 1. Now, this is not what this question even asks me for, but I need standard form to be able to graph the function, which is exactly what it does ask me for. Looking only at now the standard form, what is the center for this ellipse? -5, very good. Looking just at the equation again, what is the a value? 6, very good. And then what is the b value? B is 2. So is this a horizontal or a vertical ellipse? Horizontal. The larger number was underneath the x, so it's a horizontal ellipse. Since we know a and b, we can use a and b to solve for c. The relationship there is square root of a squared, 36, minus b squared, 4, which is square root of 32. If you do a tree for 32, it's 16 times 2, and 16 is 4 times 4, so this is 4 square root 2. That is the c value that will help me find the foci. Now, we said that this was a horizontal ellipse. So that means that the foci will take the horizontal value from the center and add the c value. So our foci are at -5 minus 4 square root 2, comma 4, and -5 plus 4 square root 2, comma 4. Where'd those pieces come from? Again, thank you for asking. This is the c value. This is the center. Why is it like added to the x coordinate instead of the y?
Why is the C in the middle?
So for this one, because this is a horizontal ellipse, let me draw a little sketch for you. Since this is a horizontal ellipse, I know that my major axis goes like this. I know that that means that the center would be here and the vertices would be here. My foci have to be somewhere in between the center and the vertices, which means we're going from the center and moving it left and moving it right instead of up and down. So to move something left and right, I have to change the x coordinate, not the y coordinate. So this is me changing the x coordinate to be less than it and more than it. In the problem before this, we added it to the y value because we had a vertical ellipse, and so we were going up and down. Now, just for our own plotting sake, this value right here, if I were to throw that into a calculator, this is approximately -10.65, and this is approximately 0.657. So just for our own plotting ability, so we know where we're going with these foci, that's our goal. So let's actually plot this. We start with the center. The center of this ellipse was at -5, 4. So we plot at -5, 4. There's our center. Our C value, sorry, just kidding. Our A value, the horizontal distance is 6. So I'm going to count 6 to the right and 6 to the left. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5. Oops, I'm off the graph, 6. That's okay. Our B value is 2. So I'm just going to make a tiny little jump 2 above and 2 below my center. My foci visually should be on the same major axis as the center and the major vertices. And if we look at negative 10.6 something, which is approximately here-ish, comma 4, and 0.657, comma 4, those are both inside the ellipse, equidistant from the center and equidistant from the vertices, if I graphed it better than I did. So the questions you're going to have today are going to ask you to graph correctly the ellipse, or select the correct graph, and give me the pieces of information correctly. Give me the coordinates of the foci, give me the coordinates of the major and minor axes, which means you're going to want to hang on to how you found these different values above, below, sideways from the center, but the center holds a lot of the information. This was also a lot for a moment. Does anyone need to ask some questions about here? I didn't even pause to ask questions about completing the square. Does anybody need an additional explanation there? Okay, fabulous. Thank you guys for listening. That was a bit of a longer day for us today. Your homework is online, so go ahead and get out your computers and log in. I want us to start practicing now with this. Or if you wanted to go watch the project video, we're going to use the last bit of class time to do something productive in regards to conics. So pick either working on the homework or looking at the project, whatever you think would be most beneficial for you. But let's knock some stuff out here.